This is EE698I, mixed signal IC design, and this is lecture number 17. In the last few classes, we have been looking at the switched capacitor amplifier, and in particular, we were looking at this variant, wherein we sample the input Vin across a capacitor C during the phase phi1, and during the other non-overlapping phase phi2, we transfer the charge to another capacitor like this. And this capacitor is reset during the phase phi1. We also saw what happens to the output when we use an OTA instead of the op-amp. So we saw how the output settles with a time constant. And also we calculated what is the total integrated noise at the output here. Right? In practice, after sampling this input here, we might also want to do some discrete time processing by passing it through a discrete time filter. Right? We'll see later about this in the course, but this is a requirement which we might need in some ADCs. Okay, so we'll see how to realize a discrete time transfer function using this switched capacitor circuits. And for that, first let's see how to implement a discrete time integrator. Because most of the practical transfer functions we might be interested in can be realized as a cascade of integrators with some feedback. Okay, and what's a discrete time integrator? That is essentially an accumulator which keeps adding the input to the existing output. Right? So if you look at the difference equation, it will look like this. The output V out of n will be the previous output sample V out of n minus 1 plus say some k times the previous input V in of n minus 1. And what will be the transfer function h of z? That will be simply k times z inverse by 1 minus z inverse. We can also have one more variant where we do not have this delay, right? That is, the input is instantly added, and we can have a delay-free accumulator or an integrator, wherein the output is the previous output sample plus some k times the present input sample. And this will realize a transfer function k by 1 minus z inverse. Okay, so let's see how to implement both of these transfer functions. So let's start with the first one. So here we can clearly see that the output sample needs to be sum of with the previous output and the current input, right? Scale by some scaling factor k. We just saw how to realize this portion, right? We know how to realize a circuit that implements V out of n equal to k times V in of n, right? That is this guy. So now let's see how to add this portion also. So what happens here in the switched capacitor amplifier is the following. So during the phase phi1, the input is sampled across the capacitor C, right? And let's say the sampled input is some V naught. And the other capacitor CF, that is reset along with the op-amp like this. Okay, and during the phase phi2, we connect the capacitor C to the virtual ground enforced by the op-amp. Right? So what happens here? In the phase phi1, the charge stored across the capacitor is C times V in, V naught, while this capacitor is totally uncharged, so it has 0 coulombs of charge. So when we connect the circuit like this during the phase phi2, both the ends of the capacitor are at 0 volts. So which means the capacitor should have 0 charge, which means the charge that it had previously, that is this C times V naught, has to go somewhere. And this obviously will go to the feedback capacitor like this. right? So the charge stored across the feedback capacitor will be the earlier charge 0 coulombs plus the new charge that is getting added by this capacitor, which is simply C times V naught, which means the output voltage will be C by CF times V naught, right? And this is how the switched capacitor amplifier works. And now along with this, we also need to add the previous output sum, right? So which means we need to make sure that the capacitor here is not reset before, right? If this is not reset like this, it will hold the output that was in the previous clock cycle, right? So this gives the equivalent circuit to be like this, where during the phase phi 1, we sample the input across the capacitor C, and during the phase phi 2, we transfer the charge to the feedback capacitor. Right? This is my Vn of t. The only difference is that we do not reset this capacitor CF during the phase phi 1. Okay, so if you look at the clock to the circuit, let's say it is like this. So this is when phi 1 is active, say this is when phi 2 is active, and so on. This falling edge of phi 1 here, they will all correspond to the sampling time instant. So let me call them as some n-1 ts, n ts, and so on. So which means the rising edge here, this will correspond to a time instant of what? That will be n-1 times ts minus ts by 2. That will be n-3 half into ts. So similarly, this will correspond to n-half into ts, right? Because each of these pulses will have a width of ts by 2. Okay. And if we look at the difference equation we want, we can see that we are interested in the output samples at nts, right? So what we need to do to get the output samples is that we need to sample the op-amp output during the phase phi 1 so that we get the output values at these time instants, right? And this is what will give us our discrete time output V out of it. So let's quickly analyze and check that we get the required output. So during the phase phi 1, that is during this phase, where the time is say n-3 half into ts to n-1 times ts, right? This is the phase. So the equivalent circuit is this, where the capacitor samples the input, the feedback capacitor remains in feedback, and this is my V. So at the end of this phase phi 1, what is the voltage stored across the capacitors? At the end of the phase, this will be n-1 times ts, right? So let me say that the voltage across the capacitor here will be Vin of n-1 times ts, right? So this is what we will call as the discrete time Vin of n-1, right? So similarly, the output here, this will be V out of n-1 times ts, and this is what is our discrete time sample V out of n-1. Okay, and again due to virtual ground, this will be at 0 volt. So during the phase phi 2, what's the equivalent circuit? We have the left plate of the capacitor C to be grounded, and we have the connection like this, right? And what is this time period? This happens during this time interval, right, between n-1 ts to n-half into ts. So this is between n-1 times ts to n-half into ts. So at the end of the phase phi 2, so we'll have the output to be V out of n-half into ts, right? And what will be the this voltage? We can find using charge conservation. So if you look at the total charge at this node, that is going to be the sum of the charges in these two plates, which is simply minus V out of n-half into ts times cf. right? And this must be equal to the total charge stored in these two plates in the previous phase, which is simply minus V in of n minus 1 Ts times C minus V out of n minus 1 times Ts into Cs. So what is the output voltage at the end of the phase phi 2? That is n minus half into Ts. That will be V out of n minus 1 Ts plus C by Cf into V in of n minus 1 Ts, right? And during the next phase phi 1, that is during this phase, what will be the output that is sampled? That will be V out of n Ts. That will be same as this fellow, right? Because between phi 2 to phi 1, the only change is that we are disconnecting the capacitor and sampling it and using it to sample the input, right? So the voltage across the capacitor CF is going to be same, and that will be this, right? So if we write the final output, we'll have V out of NTS to be V out of n minus 1 Ts, that is the previous out sample, plus C by Cf into V in of n minus 1 into Ts. So if our sampling time instants are marked at k times Ts, what will be the samples? V out of n minus, sorry, this will be V out of n, and this is V out of n minus 1 plus C by Cf into V in of n minus 1, right? So this implements the required transfer function for us of the form k z inverse by 1 minus z inverse. Okay. So similarly, you can also implement the delay-free integrator, wherein we want a transfer function of the form just k by 1 minus z inverse, right? And this can be realized by simply sampling and transferring the input charge during the same time instant, sorry, during the same phase. So what we'll do is the following. During the phase phi 2, we'll reset the capacitor here, and during the phase phi 1, we'll directly sample and transfer the output, sorry, transfer the input to the feedback capacitor like this. Okay, so this will give a transfer function of the form minus k by 1 minus z inverse. Okay, so you can analyze it yourself and confirm it. Now let us say we want to implement a more complicated transfer function, and let us say we can decompose it to be of the form k1 times z inverse by 1 minus z inverse plus k2 times z inverse by 1 minus z inverse the whole square. So let's see how we can implement this. Of course, we know how to realize this, right? This is a switched capacitor integrator. So during the phase phi 1, we'll sample it. During the phase phi 2, we'll simply transfer this to a capacitor like this, right? And of course, we need to sample it during the phase phi 1 so that we implement this transfer function, right? And how do we implement this? Well, this is just two integrators in cascade. So we'll put one more switched capacitor integrator, right? So again, we'll sample during the phase phi 1, and during the phase phi 2, we'll transfer it to another capacitor, right? Again, we need to sample this during the phase phi 1. Okay, so now we have these two outputs. We need to sum these two, right? So let's see how do we do that. Let's say I call this to be V01 and this to be V02, right? Of course, we just saw that we need to sample them during the phase phi 1. So first, let's do that. We'll sample them during the phase phi 1. This is V01 and this is V02, right? And now what we need to do, we need to add these two voltages. And how do we do that? Well, we have already sampled these two signals, right? So we have charges corresponding to these voltages. Now we just need to add these two charges, right? And we can do it by completely transferring both these charges to another capacitor And how can we transfer charge stored in a capacitor completely to another capacitor? We'll again use our infinite capacitance. Right? So during the phase phi 2, we'll connect it to an infinite capacitor realized using negative feedback like this. Okay. And of course, this capacitor has to be reset during the phase phi 1. Right? So this portion here is essentially a switched capacitor amplifier. Right? Now we have one more additional branch so that we can amplify or we can add these two signals together. So now that we have looked at the switched capacitor circuits in some detail, let us see the history behind them. So in the earlier days, when people tried to realize analog filters, which were essentially required in wireless or radio receivers, the filters were realized using active RC circuits. See something like this, see some more complicated circuitry, and some feedback like this. Okay, the bottom line is that the bandwidth of these filters, they will be inversely proportional to some R and some C, right? And on an integrated circuit, the individual values of both resistors and capacitors can change by plus or minus 10%, or in some cases even by 20%. So which means in this case, the RC time constant that can vary by plus or minus 20%, right? So which means the bandwidth of the filter here, it will not be the same that you had designed for, right? So people were trying to find a solution to this problem. And the line of thought was the following. On an IC, even though the individual values of R's and C's cannot be controlled well, what can be controlled well is the following ratios of two components, such as ratios of resistors or ratios of capacitors. Okay, so even though the individual capacitance value say changes to some 1 plus alpha times C1 here, even the other capacitor, they will also change by the same amount so that the ratio remains same, right? So people are trying to keep a constant bandwidth. So which means what they were trying is the following. They were trying to see if we can implement a resistor using a capacitor or a capacitor using a resistor, right? And of course, it is much easier and it's more feasible to realize a resistor using a capacitor, because a resistor is a memoryless element, right? So you cannot use a memoryless element to mimic an element which has memory. On the other hand, a capacitor has memory, and we can make it to look like it does not have memory, right? So it's more easy to pretend that you do not have a memory of something, even though you have a memory of it, right? So that's the idea here. So let's see how a capacitor can be used to mimic a resistor. So let's say we have a voltage source here, and I connect it to across a resistor like this. The current through the resistor is what? It's V by R. So if I look at the current across time, it's going to be V by R. Okay. So you can think of this voltage source as a reservoir which has an infinite amount of charge, right? So it can deliver any amount of current. So as an analogy, you can think of this as a reservoir of water, and let's say it has an infinite volume of water. That's an ideal voltage source. Okay. And when you connect a resistor and draw current from this, which means you are drawing charge constantly from this voltage source, right? So here charge is analogous to water here. So the equivalent action is to do something like this, right? So we can connect, have an opening here so that we have a constant flow of water here. Okay. And now let us say we want to mimic this action using a capacitor. Right. So again, we have the infinite reservoir. And what is a capacitor? You can think of a capacitor as a small bucket, right? it can hold charge, or in this case, it can hold a small amount of or small volume of water, right? And with this bucket, what we want to do, we want to try to take water out of the reservoir. And how can we do that? Well, first we can fill the bucket with this water and then throw the water out, right? And we keep doing it continuously, right? And electronically, how we'll do that? Well, first we need to charge or fill water onto this bucket. So we'll connect the capacitor to the voltage source, say during one phase. And next, what we need to do, we need to throw out the water we had filled, right? So I'll connect the capacitor to ground during the phase 5, right? So now, if we look at the charge, how will it look like? First, let's look at the charge in the case of a resistor, right? So we have a constant current. So which means if you look at the charge as a function of time, it's going to be linearly increasing, right? Because charge is an integral of the current. So this is the case when we have a pure resistor. So now let's see what happens with the capacitor. So with the capacitor, initially the current, the charge that is pushed out here is 0, right? And once the capacitor is charged to the voltage, in the next phase, it can dump out some charge, right? And this charge is equal to C times V, right? And again, there will be no charge coming out. And once the capacitor is charged, it will again dump some amount of charge, right? So next it will be 2 times CV, and so on, right? So essentially we'll have this kind of a waveform for the charge, right? And if you look at the waveform for the current, how will it look like? Current is essentially derivative of the charge here. So we'll have an impulsive current like this every time the capacitor is dumping the charge to ground, right? So let me draw it separately. So if we look at let me draw it here itself. So with the resistor, we had a constant current, V by R, right? Now with the capacitor at these instants, we have an impulsive current, right? And if we make sure that the average of this impulse time is equal to V by R, then we would have mimicked this action of resistor, right? And of course, if you look at the charge waveform, ideally we have a linear ramp like this with the resistor. And with the capacitor, if we keep doing this commutating action, that is switching action, at a much faster rate, the charge profile will look like this, right? And if we keep doing it at a faster and faster rate, you might not be able to find any difference between a resistor and a capacitor. Okay, so that's the idea. So now let's find what is this equivalent resistance that the capacitance is realizing. So let us say this is the clock we have. Again, let's say this is phi1 and phi2. The total time period is Ts. So during the phase phi1, the capacitor is getting charged to C times V, right? That is the charge the capacitor has. And during the phase phi2, it is pushing out the charge, right? So the total charge that is pushed out is C times V, right? So during the entire period of Ts, the total charge that is pushed out is C times V. So the average current is C times V by Ts, right? So which means this is simply C times V times Fs, okay? And this is the average current, right? So if you want to write it in terms of V by some R average, what is the average resistance? It's going to be 1 by Fs times C, okay? So the bottom line is that if we make sure that the switching frequency here is much faster than the rate at which the input itself is changing, then both of them will be more and more identical. Okay, so now let's see how we can use this information. So this is the basic building block in an active RC filter, which is essentially an integrator, right? And if you look at the transfer function, it's minus 1 by SRC, right? If this is input and this is output. Okay, and here we can find that the slope of the integrator or the scaling factor for the integrator is 1 by RC. And as we saw earlier, the values of R and C can change, which means even this gain of the integrator will change. So now we will try to replace this resistor by the switched capacitor we saw. Right, so this is the phase phi 1, this is the phase phi 2. Okay. And let's say we sample the output during the phase phi 1. Okay, so this is the clock. This is again phi 1, phi 2, and so on. And let's say I call the falling edge of phi 1 as the sampling instant. Right, so that's why I'm sampling the output also during the phase phi 1. Right, so what will happen during the phase phi 1, if this is Vin of t, the capacitance C here will get charged to Vin of, say if I call this instant as n minus 1 ts and this as n ts. So during this phase, the capacitor will get charged to Vin of n minus 1 ts, right? And during the second phase, we'll connect it like this, so which means it will transfer this entire charge to the capacitance, right? So the charge stored in C will be C times Vin of n minus 1 ts, right? So that is the charge in the phase phi 1. And in the phase phi 1, CF is charged to what? It is charged to V out of n minus 1 times ts, right? So the charge in CF during the phase phi 1 is CF times V out of n minus 1 ts. So during the phase phi 2, we connect the capacitance like this. And since this is virtual ground, this capacitor will transfer all its charge to CF. So the total charge stored in CF is this, right? So the final output voltage at the end of the phase phi 1, that is the next phase here, that will be V out of n times ts. And this will be equal to the total charge, which is this, divided by the capacitance CF. So what we have is V out of n to be V out of n minus 1 plus C by CF times Vn of n minus 1. Right, so this essentially realizes the transfer function C by CF into Z inverse by 1 minus Z inverse, right? And if we make sure that the switching frequency here is much faster compared to the rate at which the input signal is varying, then the output samples here, if you look at the output voltage here, it will change only at TS, 2 TS, 3 TS, and so on, right? So if let us say ideally the output here looked something like this, okay, the output of this circuit will do something like this. So it might go here, and then during the TS it will change like this. Okay, during 2 TS it will go like this, and so on. Okay. Again, if you reduce this spacing of TS, then this will mimic more and more like the actual continuous time signal, right? And of course, instead of using this kind of a switching circuit, which has the problem of signal dependent charge injection, we replace this branch by something like this, right? Right, so we had during the phase phi 1, we have 2 switches here. This will be the switch clocked at the early clock phase so that we do not have signal dependent charge injection, and we do the charge transfer like this. So there is one more reason why this kind of switching is not preferred. So let's look at that. So again, if you look at how a capacitor is realized on an integrated circuit, we essentially have two parallel plates like this, right? So I'm considering a simple min capacitor. And of course, we also have the P substrate here, which is usually connected to ground. Okay. And along with the required capacitance C, you can clearly see that we can also have a capacitance from this bottom plate to ground, as well as a parasitic capacitance from the top plate to ground. Okay, so let me call them CP1 and CP2. Right? So now, in the switch capacitor integrator we saw, this was the circuit, right? Now, along with the actual capacitance C, we'll also have parasitic capacitance associated with both the top and the bottom plate. Now, the parasitic capacitance associated with the bottom plate is not a problem because the bottom plate is grounded. But the parasitic capacitance from the top plate, CP1, will create an issue, right? Because now the total capacitance is no longer C, it is C plus CP1, right? So it is equivalent to changing this capacitance C to C plus CP1. So which means the final transfer function here, instead of being C by CF into Z inverse by 1 minus Z inverse, it will now be C plus CP1 by CF times Z inverse by 1 minus Z inverse, right? So in the earlier case, we just had ratios of these two capacitors, and as we saw earlier, this ratio can be extremely well controlled. But now, along with that, we also have this additional parasitic capacitance, right? So this will again change our transfer function. Okay, so that is why this kind of switching is not preferred. And this integrator is also called as parasitic sensitive switched capacitor integrator, right? Because the transfer function you realize is sensitive to the parasitic capacitance. And if you look at the switching circuit we had the equivalent, we had the switching circuit like this. Right? So here again, we'll have parasitic capacitance associated with both the top and the bottom plate. So we have CP1 here, say, and let's say this is CP2. Okay. So now what will happen? Well, during the phase phi 1, we have the equivalent circuit like this. Right. So the parasitic capacitance associated with the bottom plate will not create an issue because it's completely discharged. While we still have the parasitic capacitance CP1 getting charged to the input voltage, right? But during the charge transfer phase, what happens? This is the circuit we have, right? So the capacitor is connected like this, right? So which means this capacitance CP1, which was here, is now completely shorted, right? So which means this is not going to create any issue, right? And the only capacitance that could create issue is CP2 here, but you clearly see that CP2 was initially completely discharged. So it is not going to add any additional charge, like any additional charge here, right? So the transfer function will be C by CF into Z inverse by 1 minus Z inverse, right? And this is insensitive to the parasitic capacitors, right? And so this is called parasitic insensitive switched capacitor integrator. Okay. And one fine point to be noted here from this figure, you can clearly see that the parasitic capacitance from the bottom plate will be much higher than the parasitic capacitance from the top plate, right? Because the bottom plate is more closer to the substrate. right? So CP2 is usually much greater than CP1. Okay. Before concluding, let's take a look at a small example so that you get an idea as to how to solve and analyze such switched capacitor circuits. So let's say this is the circuit we have. We have input voltage V in of t. It's connected to a capacitor C1 like this. This is phi 1 and phi 2. Let's say we have one more capacitor C2. And let's say my clock is looking like this. And this is phi 1, phi 2, and so on. Okay. And as usual, let's define the falling edge of phi 1 to be our sampling time instant. So I'll define this as the time t equal to n minus 1 ts. This to be n ts. So this will be n plus 1 ts and so on. And let us say we are interested in finding the voltage across the capacitor C2, right? Sampled at the end of every phi 1. Okay. So if this voltage is called V out, let me push it here. If this is V out of t, what we are interested in are the samples V out of n, the discrete time sequence, which is essentially the voltage V out at every n ts, right? So let's see how we can find and solve this. So during the phase phi 1, that is during this time period, the equivalent circuit is this. The capacitor C1 is charging the input and C2 is open like this, right? So at the end of the phase phi 1, that is at this time instant, the voltage stored across C1 is what? It is simply V in of n minus 1 times Ts, right? Similarly, the voltage across C2 is V out of n minus 1 Ts, right? So again, let me just push it here. So during phi 2, what happens? We have the two capacitors connected in parallel because the switch is closed, and phi 2 is this time interval. So at the end of phi 2, so at this time instant, so this time instant is what? This is n minus half into Ts, right? So let's find the output voltage first at this time instant. And this is C1, this is C2. So the output voltage is what? That is going to be V out of n minus half into Ts, right? So, and how we can find this voltage? We can find it using charge conservation. And since we are connecting these two capacitors like this, there will be charge transfer between charge distribution among them. And the total charge at the end of the phase phi 2 is what? It is V out of n minus half into Ts times C1 plus C2, right? And this will be equal to the charge in the previous phase, which is simply V in of n minus 1 times C1 plus V out of n minus 1 times C2. So this will be C in into V in of n minus 1 Ts plus C2 times V out of n minus 1 Ts, right? So the voltage V out at the end of the phase phi 2, that is the time instant here, will be V out of n minus half into Ts. This will be C1 by C1 plus C2 times V in of n minus 1 Ts plus C2 by C1 plus C2 times V out of n minus 1 Ts, right? So, which means the voltage in the next phi 1, that is at the end of the phi 1 here, what will that be? That is V out of n Ts, right? And what will that voltage be equal to? Well, that will be same as the voltage here, right? Because from phi 2 to phi 1, we see that the capacitor C2 is remaining the same. That is, the voltage across the capacitor is not changing, right? Because there is no additional charge getting pushed in or nothing is pulled out, right? So V out of nTs is same as this. And according to our definition, this is essentially V out of n. So this is simply V out of n. And what is it? That is C1 by C1 plus C2, V in of n minus 1, the discrete time sample at n minus 1th instant, plus C2 by C1 plus C2 times V out of n minus 1. Right, so let me write it once again here. V out of n is C1 by C1 plus C2, V out of n minus 1, plus C2 by C1 plus C2 times V in of n minus 1. So what is the transfer function that is getting implemented? That is V out by V in of Z. That is simply C1 by C1 plus C2 times Z inverse by 1 minus C2 by C1 plus C2 times Z inverse. Okay. And you can clearly see that this is also trying to implement an integrator, right? But instead of having the denominator of the form 1 minus Z inverse, we have something of the form 1 minus alpha Z inverse. Okay. So this is also called the lossy integrator. Okay, because for an ideal integrator of the form Z inverse by 1 minus Z inverse, if you apply an impulse, the output is what? It's simply U of n, right? It's going to be constant. But for an integrator of the form Z inverse by 1 minus alpha Z inverse, you know that the impulse response is alpha power n U of n. So it's going to start from 1, but eventually decay to 0. Right? Let's stop at this point and continue from the next class.